with that, let me call our third presenter, the Best Paper Award winner. Yes. So please, Thomas. The paper will be presented by Thomas Alfroy. The paper is the next generation of BGP data collection platforms. So Thomas, oh, by the way, this is Thomas' papers, right? So Thomas is a third-year PhD student at the University of Strasbourg. He's about to defend his thesis. It will be a nice one. His research consists of building systems to improve internet measurements and security. So the floor is yours.
Thanks a lot. OK, should work. So hello, everyone. I am Thomas Alfroy from Strasbourg University. And today, I'm going to show you that many BGP events remain off our radars. And I will show you how can we reduce these visibility gaps. I would like to start this presentation with this curve. So this curve presents the evolution in the number of collected BGP routes over the last 2 decades. And we can clearly see that this evolution follows a quadratical pattern. And the number of collected BGP routes has grown so much that now approximately 1 terabyte of raw data is collected every day. And as the internet is in continuous expansion, we can expect this number to continue following this quadratical increase. While both researchers and network operators get the BGP data as granted, BGP data collection platforms such as Rypris and Raudius are currently facing data management challenges and are responding to this quadratical increase in the volume of collected data by limiting their coverage, as stated in these 2 blog posts written by Rypris operators. And this limitation of the coverage creates dangerous visibility gaps. And in the meantime, even with the current volume of data that is collected, users often do not have the required resources to process all the data. And they often resort to arbitrarily sample, which further make the visibility gaps even worse. So we surveyed 8 authors of top research papers, and 7 out of them said that given more time and resources, they will have used more BGP data. However, research and commercial BGP monitoring tool cannot afford these visibility gaps. So the BGP data is used to monitor the internet routing ecosystem. And some of these tools are used to monitor critical services, and they are used for cybersecurity purposes. So for instance, to detect BGP hijacks. So the question now is, what is the impact of these visibility gaps on these critical tools? So 1.2%. So this number corresponds to the vantage point coverage of the current BGP data collection platform, so Rypris and Raudius in our case. So BGP data is collected from vantage points, or VP, which consists of a router located within a single autonomous system, or AS, which set up a BGP session with a BGP collector and export all of its best routes to a BGP data collection platform. So here, the vantage point coverage corresponds to the percentage of ASs that share their BGP data with a BGP data collection platform. And despite the deployment of new vantage points over time, as the internet is in continuous expansion, this vantage point coverage has remained flat for now 2 decades. And a low vantage point coverage is a problem. So because of the inherent path-hiding nature of BGP, each vantage point only has a partial view over the internet routing ecosystem. If we are using a little analogy here, it's like if we want to monitor the Earth's surface from satellites. So each satellite only sees a small portion of the Earth's surface. And as we have a limited number of satellites, we may miss a lot of very important information. So because it is hard to precisely know what we are missing from vantage points that are not deployed, so basically because we do not have the ground truth, we measure the impact of the low Rypris and Raudius vantage point coverage on 3 use cases using simulations in a controlled environment. So let's focus on the first use case, peer-to-peer AS link observation. So here we focus on peer-to-peer links as they are more challenging to observe. So on this graph, we present in the y-axis the percentage of peer-to-peer links that we can observe in our simulation according to the vantage point coverage in the x-axis. So here, the vantage point coverage corresponds to the percentage of ASs in our simulation from which we will use the data. And we will now show that with the current write and reduce vantage point coverage, we may miss a lot of very important information. And in fact, when the vantage point coverage is approximately 1%, we may miss 84% of the peer-to-peer links. And this result suggests that we should have at least one order magnitude more vantage point. Because here, for instance, if we have a vantage point coverage of 50%, we may miss only 11% of the peer-to-peer links. So we also did the same experiments with other use cases where we observe similar results. And for instance, the last result means that any of the BGP monitoring tool will miss 24% of the type 1 hijacks. So if you want more details about this analysis, you can refer to the paper. So the current data collection strategy for BGP consists of collecting all the routes, but from a few ASCs. However, in this presentation, we will explore a new paradigm for BGP data collection in order to reduce these visibility gaps. We will present GIL, a system that collects a few routes, but from many ASCs. Spoiler alert, you can already start peering with GIL at bgproutes.io if you're interested in contributing to this project. I will now show you how we made this paradigm shift possible. So we will start by making a key observation, which is that BGP routes are often redundant. I will use this gadget to show you how BGP routes can be redundant. So this graph represents a 7 AS mini-internet topology, where the ASs are interconnected by either peer-to-peer links, represented by a line, or customer-to-provider links, represented by an arrow. The routing policies are configured according to the Gao-Rexford model, and thanks to Lechin talk this morning, I don't have to explain you what is a Gao-Rexford model. In this scenario, AS4 will announce two prefixes, prefix 1 and prefix 2, and AS6 will announce one prefix, prefix 3. We will consider the deployment of two vantage points, one in AS2, one in AS6, and both these vantage points will export all of their best routes to a BGP collector. Let's now consider two events that will trigger new BGP routes. First, a failure on the link between 2 and 4, and second, a hijack intended by AS7 targeting prefix 3. So because the primary path from AS2 to prefix 1 and prefix 2 uses the fade link, vantage point 1 will receive two new routes, one for prefix 1, one for prefix 2, with a new AS path circumventing the failure. Similar case for vantage point 2, which will receive also two routes with a new AS path circumventing the failure. If we now take a look to the collected routes, we can clearly see that they exhibit some redundancy because they are sharing some very similar BGP attributes. But in addition of this problem of having redundancy in our collected BGP routes, we have two other problems. First, the failure here is visible in only one direction, which is problematic when applying typical failure localization algorithm. And second, none of the collected routes enable to detect the hijack. Now, I will show you how redundancy in BGP data enables an overshoot and discard collection strategy for BGP. So the overshoot and discard is a new paradigm for BGP data collection that works in two steps. First, overshoot, meaning that we will collect data from as many vantage points as possible in order to prevent missing important information. If we use again this scenario, instead here of collecting data from 2 vantage points, we will collect data from 5 of them. Obviously, we will end up with more collected routes, but the additional collected routes enable very interesting inference, because we are now able to see the failure in both directions, and thanks to the routes collected by vantage point 4, we are now able to detect the hijack. However, obviously, with this scenario, we are collecting more data compared to the current BGP data collection strategy. And this is why we are now applying the second step of our new paradigm, discard, meaning that we will filter out the redundant routes in order to reduce the volume of data that is collected. So here, once again in this example, instead of collecting all the routes from all the vantage points, we'll deploy filters on our BGP collector that aim at discarding the redundant routes. So here, instead of collecting 6 routes, we'll end up with only 3 routes collected. But as we discarded only redundant routes, we are still able to see the failure in both directions and to detect the hijack. That's wonderful. Unfortunately, because of the deployed filters, some objectives become unachievable. For instance, if a user wants to know if prefix 1 and prefix 2 are sharing the same BGP attributes, this is not feasible with the retained routes, sorry. And this is why we need to be really careful when generating filters that aim at discarding the redundant data. I will now present you the star of this presentation, GIL, a system that measures the redundancy in BGP data and uses it to generate filters that retain only the most useful bits of the BGP data. So GIL collects BGP data from a custom BGP collector that we developed and that is optimized to collect BGP routes. Such that GIL can handle more than 10,000 BGP sessions on a single commodity server. Then GIL deploys filters in each BGP collectors. So GIL deploys filters in each of our BGP collectors. So here, a received route that matches any of the deployed filters is discarded. Otherwise, the route is retained and stored in our database. GIL also uses an orchestrator, which main task is to generate the filters. And this filter generation process is data-driven, as it uses all the data collected from our BGP collectors, but on a limited time period. And this filter generation process is GIL's fundamental algorithmic contribution. This process works in 3 steps. The first one is to identify the redundancy in the past BGP data, which is a very challenging task, as there is no consensus on how to define the redundancy in BGP data. The second step is to predict future redundancies in BGP data. And fortunately for us, this is feasible, as we demonstrated in the paper, that the redundancies in BGP data are stable over time. Third and last step consists of generating filters that retain only the most useful bits of the BGP data, which is also a challenging task, because we cannot predict what users want to do with the data. So it is very hard to predict what useful means for the users. So here, the first step for our orchestrator is to identify the past redundant routes. However, we showed previously with our example that discarding all the redundant routes may render some objectives unachievable. And this is why GIL uses anchor vantage points, which is a subset of the vantage point that contains the least redundant vantage points from which we will keep all the data, such that objectives that, for instance, require an entire routing table are still achievable. Then GIL will identify the space of possible redundant routes and anchor vantage points. And finally, GIL generates filters that discard the future redundant routes only if they don't come from an anchor vantage point, meaning that we will keep all the data from the anchor vantage points, even if redundant, such that objectives that require a redundant signal in BGP data are still achievable with the retained updates. Obviously, GIL needs to regularly refresh the filters in order to maintain them accurate over time. In this presentation, we'll focus only on GIL's process to identify the past redundant routes. If you are interested in any other process, you can refer to the paper. So the idea here is that GIL classifies a BGP routes as redundant if it is not required to reconstitute the other routes. So it can be seen like an image compression algorithm, but for BGP data. So here we will have an original set of BGP routes. So if we are using our analogy, a set of pixels, so basically an image, that can be compressed into different subsets. However, different subsets of the same size may not be as useful as each other. For instance, we can clearly see that the first option contains more representative pixels, while the second contains less representative and more redundant pixels. So it is easier to reconstitute the original image from the first option. And this is the kind of compression algorithm that GIL is applying on BGP data. So good news for us, since BGP routes are highly redundant, many many BGP routes can be discarded without losing critical information. So here on this graph, we present in the y-axis the reconstitution power, which corresponds to the proportion of original routes that we can reconstitute from one of its subsets, according to the percentage of retained routes in the x-axis. And we can clearly see that this reconstitution power is always pretty high, because here we can reconstitute 94% of the original routes from only 7% of them. Note that these results are produced using real BGP data collected from write and route views and not through simulations. So now I will show you that GIL positively impacts many studies, both on the long and short term. So we estimate GIL long-term impact using simulation on a mini-internet topology with 6,000 ASs. The idea here is to compare the original approach, which consists of collecting all the routes from 2% of the ASs, against GIL collecting data from 50% of the ASs, but discarding 96% of the collected data, such that the volume of data collected by GIL and the current approach are similar. We evaluate GIL's impact on 3 use cases: topology mapping, failure localization, and hijack detection. And we can clearly see that for all of these use cases, GIL significantly improved the trade-off between volume of collected data and information inferred from the collected data, because we can here see 3 times more peer-to-peer links, localize twice as much failures, and detect 9% additional hijacks. GIL also has a significant impact on existing studies, as the algorithm used to identify the redundancy in BGP data can be used by the user to sample the BGP data in a smart fashion. For instance, with the exact same volume of data collected from write and route views, GIL improves CAIDA AES relationships by finding 16% additional AES relationships. Similarly, GIL helps DIFO to detect a system that detects forged origin hijacks in the wild to find 31% additional suspicious cases of forged origin hijacks. Obviously, there are many more benefits of using GIL, and if you want to see very interesting experiments, you can refer to the paper. I will conclude this talk with a bit of advertisement. A prototype of GIL is currently running at bgproutes.io. So the idea of GIL is not to replace existing BGP data collection platforms, but to propose an alternative way of collecting the BGP data. In fact, we have bootstrapped our platform with data collected from write and route views, and we are really grateful to them for this. Why should you peer with GIL? Because this is entirely automated, and it will take you no more than 5 minutes to set up a peering session. Then we always want the data collected by GIL to be beneficial for the community. And finally, we envision to forward interesting data for operators prior to discarding, such that operators can benefit from a higher coverage on their prefixes. Now, if you have any question or feedback, I will be happy to discuss. Thanks for your attention.
Thank you, speaker. Yes, Matt.
Hey, Matt Rowan from Adelaide. So thank you for this. This is very cool. I really like the idea, and I can see lots of value in it. One of the things I'm sort of interested though in is we've learned a lot about BGP from the dynamics of it, the churn that happens as you go to convergence, particularly about things like convergence. Is that still going to be there, or is that going to be reduced?
So yeah, okay. So you mean we still be able to study the BGP convergence with data collected by GIL?
Yeah.
Okay. So the idea is that here we keep the data from these anchor vantage points. So objectives that requires redundancy in BGP data. So for instance, studying the convergence, they will still be achievable. But let's be honest, I cannot ensure 100% that all the possible use cases will be feasible with the data collected by GIL, which is actually also the case with the current BGP data collection infrastructures. Does it answer your question?
Almost. I guess part of the question is, so CBGP won't show you the true dynamics you would see in the wild. It will show you the end state. So I guess the transitions you go through to get to the end state, it's hard to know whether they might get lost partly, like you might not see all the withdraw announce.
No, you will see this. You will still see this because the filters deployed by GIL are on a per prefix granularity. meaning that you will see all the data from the prefix that are retained. So if you have this update, withdraw, update, withdraw, update, withdraw for this prefix, you will still be able to see it.
Okay, cool.
Next question.
I just have a clarification question. Thank you very much. This is very interesting. But you said you had tried other parameters for GIL. I just wondered if the numbers that you showed there, the 50%, were those the best? The parameters you showed were the ones that gave you the best results? Is that
obviously,
correct?
the parameter that gave us the best result is 100% vantage point coverage. So in the paper, as I mentioned, we studied other parameters. Obviously, we do not, with, for instance, a vantage point coverage of sorry, 10%, we do not have as huge improvements. We still have a big improvement. If I remember correctly from the paper, we are able to see 80% more peer-to-peer links compared to the current approach when collecting data from 10% of the vantage points, but discarding 80%. Such that the volume are matching.
So I guess the question is, this was the sweet spot in terms of amount of data and coverage, or how did you pick the parameters that you showed? That's what
here, the 50%?
Yeah.
You mean the discarding 96% of the data? Because this parameter is selected automatically by the system.
Okay.
Because the different vantage point coverage, this is just a test to see what is going to be the impact of GIL when we will have such a vantage point coverage. So this is pretty arbitrary, to be honest.
Okay.
This is just for evaluation purposes.
Thank you.
We run out of time, but we can get a very quick question and answer.
Okay, hi, I'm Anish Sheikh from Google. Maybe it's a slight follow-up to your last comment, and I'm happy to take it offline if we need to. It's a little bit odd to me the way that we're characterizing the benefits of GIL, not because it is not doing what it's setting out to do, but the real problem that we have, as I think you point out, is the lack of sufficient coverage in the vantage points, right? So I'm curious if we're going to see increased coverage, because your simulation-based comparison, where you assume 50% coverage of the fake internet that we're simulating, we're nowhere close to that. We're still at the current approach where we have 2% coverage.
Yep.
So it's, while this is solving a really important problem in terms of data redundancy and storage overheads and all the things that we get from it, it seems like we still have the big elephant in the room, which is really about vantage point coverage in order to get a better view of BGP. So I'm curious if maybe I'll ask you offline if you think that GIL might help us, work with other operators to get more vantage points deployed.
Actually, so GIL is designed to solve the operational problem of having like an order of magnitude more vantage points. But there is still the human problem of incentivizing the operators to set up a peering session. So for this, you can go to our website or see our paper. We are proposing some potential incentivize, but this is definitely an entire paper subject. There is still a lot of work to do.
All right, thank you.
Thank you. Let's thank the speaker again. Great presentation, by the way.